Welcome to UVU CS3060, Lecture 6.8, where we talk about the monitor. Now, monitors are very high-level abstractions, usually provided by a language, to give some effective mechanism for process synchronization. It is typically an abstract data type, thus is usually found in object-oriented languages. Internal variables are only accessible by codes, by functions or methods within that particular abstract data type. Only one process may be active within a monitor at a time. So you have various procedures. These procedures can only be accessed by, the whole monitor can only be accessed by one process at a time. So process 1 can access procedure 1, but no other processes can access any other procedures to make this work. Now, mind you, monitors are not always powerful enough to model some synchronization schemes, but they are very helpful. Here's a schematic view of what a monitor does. You have a linked list of processes, an entry queue, that can come in and access a particular object in the shared data. Only one process at a time can perform operations and access shared data, and shared data can only be accessed through these operations. Now, there is a concept called a condition variable. A condition variable is very much like a semaphore. You have a wait and a signal operation. In most cases, a condition variable that is being waited for will block until another process calls signal. And when signal is called, this will unblock and lock a mutex at the same time in one atomic operation. Signal resumes one process that invoked the wait. If there are no processes waiting, then there is no effect on that particular variable. You can implement in a non-object-oriented language a monitor using condition variables, where you can have queues associated with these condition variables, and then the entry queue would perform the wait and signal operations on these particular condition variables. So when it comes to condition variables, if process P invokes signal and process Q is suspended and wait, what should happen? Well, we know that Q and P cannot execute in parallel. If Q is resumed, then P must wait. So we have in this particular case a couple of options. We can have the signal and wait, where P waits until Q leaves the monitor or waits for another condition. So we have signal and wait is just simply P waits until Q leaves the monitor. Signal and continue is we have Q is waiting until P leaves the monitor or it waits for another condition. Now, languages have different ways of handling this. There's concurrent Pascal, which actually performs a version where P executing a signal immediately leaves the monitor and Q is resumed. But we do have monitors in other languages, such as Java, C#, and Mesa. Now, can we implement a monitor using semaphores? Certainly. You'll have two semaphores, a mutex semaphore and a next semaphore. And so when we have each procedure will have a wait for a mutex, perform its function, and if the next count is greater than 0, it'll signal the next, otherwise it'll signal the mutex. So we can implement a monitor with this, and every function would have to do these particular lock and unlock when they start. And this will ensure the mutex within the monitor. How do we do this with a condition variable? Again, we have a semaphore, and now we have a condition variable count. And what we increment count and make sure that we can signal the next If count is greater than 0, it will signal next, and then otherwise it will signal the mutex, then perform the wait. And here's where the signal, if the count is greater than 0, it'll increment the count, perform a signal on that semaphore, wait for next, and then perform a next count of a decrement next count. So, if we have several processes queued on condition X and the signal is executed, which should be resumed? Well, sometimes first come, first serve is not adequate. And so we can create what is called a conditional wait of the form X wait C, where C is a priority number. And so the process with the lower number, the highest priority, is scheduled next. So here we can have priority-based monitor actions. Now we can use that that priority to help us acquire a particular resource, to specify how much time a process plans to use that resource. So if a resource plans on using a resource for a long period of time, that will set the longer the time, the lower its priority becomes. If it's planning on accessing it very quickly, the higher it becomes. And so we can see here that we're setting priorities based on time with an acquire and release function that allows us to do prioritized allocation through a monitor. And this ends lecture 6.8, where we talk about the monitor.